Okay, so tonight's session is going to be a review session for your exam this Friday, which is on chapters 15, buffers and titrations, and chapter 16, which is our other equilibria classes. Okay, so again, this is a long answer exam. It's actually the only exam that you will see chapter 15 and 16 on until your final exam. Okay, so you won't additionally get a multiple choice exam on this until the final. So that being said, I'll kind of talk about what I'd expect to see on the exam at the end, but we're going to jump right into the challenge problems that I gave at the end of Monday's session before going through a total content review. Okay, so Monday I gave, I believe, 5 challenge problems. Okay, so this first one is, all of them have to do with chapter 16, but this first one's a pretty classic multiple choice questions relating to chapter 16 and selective precipitation. Right, so we have a solution that is made of lead sulfite, right? It's 0.15 molar of that salt, and then 0.18 molar of copper sulfite. Okay, now from here, we're told that solid sodium iodide is added, okay, and that the volume won't change. And the volume not changing is kind of significant because if the volume changed, these molarities of lead sulfite and copper sulfite would also change. And then you're given some Ksp values for copper iodide and lead iodide. And so question 1 asks which salt will precipitate first, and then the second question asks, what's the concentration of iodine when lead iodide starts to precipitate? Okay, and so here, what you'll kind of notice is for question 1, right, they're asking what salts will precipitate. So if a salt will precipitate, they have to give you the Ksp of those salts. Okay, and so you're given 2 Ksp values, one for copper iodide and the other for lead iodide. So that right away should tell you that choice A and B are incorrect, right? These are salts that are originally added, right? But the only reason that lead sulfite and copper sulfite are important is just it allows you to get your lead ions in your copper ions into the solution, right? The sulfite is extremely irrelevant in this problem. Okay, and so really you're trying to figure out here which one will precipitate first, copper iodide or lead iodide. And so really, and while trying to answer question 1, you'll actually have to answer question 2 as well. Okay, so all of my work will be on here. Okay, so we start off with 0.15 molar lead sulfite, right? And so that means that we're going to have 0.15 molar of lead from that, right? We also have some sulfite from it, but again, we don't care about sulfite in this problem. Okay, we additionally have 0.18 molar of copper sulfite. Okay, now something to be very careful of is there's 2 moles of copper per 1 mole of copper sulfite. Okay, and so when you do your conversion, right, you would actually find that the molarity of just copper ions is actually 0.36 molar. Okay, and again, that's because it's a 2-to-1 ratio. Okay, this point here again kind of says that you should pretty much immediately eliminate A and B, right? Again, they have to give you Ksp values for salts that can precipitate. Okay, and so now we're going to look at each salt individually. And I do apologize, I did forget to say, I did mess up my answer choices for question 2. When I came up with the answer choices, I thought choice C was correct, but I accidentally plugged in 0.25 molar instead of 0.15 molar. Okay, and so if you did this correctly, you should have gotten this answer at the bottom. Okay, and if you got that, you did the problem completely correct. That was just a slight calculator error by me, so I apologize. Okay, so I'm going to start first with copper iodide. Okay, so it's a solid, and it's going to split into its 2 ions. Okay, I'm going to form my ice table, and I'm going to have an initial amount of copper, right, equal to the amount that was added from copper sulfate, right? So my initial amount of copper is 0.36 molar. Okay, and I'm going to assume I have no initial amount of iodide. Okay, so from here, I'm going to have a change, right? And remember, in this chapter, we use S for change. Okay, and so I'm going to add S to my product side. So plus S for copper, plus S for iodide. Okay, and so at equilibrium, my concentration of copper ions should be 0.36 plus S, and my concentration of iodide should just be S. Okay, so now that I have my equilibrium amounts, I'm going to set it equal to my Ksp. So my Ksp for copper iodide is 1 times 10 to the negative 12th, which is going to be equal to the concentration of copper times the concentration of iodide. Okay, and realize that they're both raised to the first power because their coefficients in the balanced chemical equations are both 1. Okay, so moving down, I'm just going to plug in my equilibrium concentrations of each, and then I'm going to ignore S, specifically the S that is added to 0.36, right? Because we're going to acknowledge that this value of S is so small that it doesn't actually affect this 0.36 value. And so I ignore it, changing 0.36 plus S to just 0.36, and then it makes it just a little bit easier to solve for S, which I can find is 2.78 times 10 to the negative 12th. Okay, and so that, remember, that is the concentration of iodine needed for me to start precipitating copper iodide, right? Because as soon as you go above, this is the amount of iodide needed to reach Ksp, and as soon as you increase any amount higher than this molarity of iodide, then Q is greater than Ksp, the reverse reaction is favored, and you're going to form that solid, that precipitate. So let's do the same thing for lead iodide. Okay, so lead iodide solid will split into lead 2 plus ions plus 2 iodine ions. Okay, my initial amount of lead coming from lead sulfite is 0.15 molar, and my change is going to be plus S for lead. And you'll notice for iodine, it's actually plus 2S, okay? Plus 2S, because its coefficient is 2. And so at equilibrium, our amount of lead is 0.15 plus S, and our amount of iodide is 2 times S. And so I'm going to plug this into my Ksp equation. So the Ksp, which is 7.9 times 10 to the negative 9th, is equal to my concentration of lead times my concentration of iodine squared. Okay, and so I'm again going to plug in my equilibrium values. I'm going to ignore S for the 0.15 plus S, because again, we're going to say S is so small it doesn't affect that value. And we can solve and find that the solubility of lead iodide, or the amount needed, is 1.15 times 10 to the negative 4th. Okay, and sorry, let me just check what the question is. And so it says, what is the concentration of iodine? Okay, and so I actually made 2 small errors here. Okay, so the first one, I got a different value because a multiple choice question wasn't here because I plugged in a different value. Okay, but the equilibrium concentration of iodine is actually 2 times S. So I apologize here. It should actually be 2 times this value is the concentration of iodide needed to start precipitating, right? Because again, concentration of iodine, when we plug it in, it's 2S. So it should actually be 2.3 times 10 to the negative 4th. Okay, and I'll put that in the chat so that people have the correct answer. But are there any questions on this one? I do apologize for that. Should be. Okay, do be wary of that. That is a very common mistake that sometimes people forget. Sometimes you'll solve for just S and you'll give that as the answer. Okay, but again, I asked, what is the concentration of iodide needed to start precipitating this solid, okay? Which means what is my concentration of iodine at equilibrium, basically? And so at equilibrium, iodine is actually equal to 2 times S. So it's 2 times this value. Okay. Any questions on here before moving on to the next one? Okay. So here's another multiple choice question that was pretty much right from my exam. So you have two kind of unknown compounds that we're just going to denote with a bunch of variables, La2 and Ly. Okay, and you're told that they have similar molar solubilities in water. So you're told that the Ksp of La2 is 2.8 times 10 to the negative fourth, and so you're asked, what is the Ksp of Ly? Okay, and the key to this point is that they have, the key to this question is the fact that they have similar molar solubilities, right? So when you solve for S in these ice tables, that represents the molar solubility. And so they're saying that these two compounds basically have the same value for S. Okay, and so knowing that, right, we can use this La2 compound to then help us find the Ksp of that Ly compound. So I'm first going to turn my attention to La2. So La2 solid will split into L2 plus ions and 2A minus ions. Okay, we're going to assume we have no initial amount of either ion, and then our change is going to be plus S for L2 plus and plus 2S for A, because again, its coefficient is 2. Okay, so now knowing my equilibrium amounts of both these ions, I'm going to plug it into my Ksp equation. So my Ksp equation is my Ksp, 2.8 times 10 to the negative fourth, is equal to my equilibrium concentration of L2 plus, which is S, times my equilibrium concentration of A squared. Okay, so it's going to be 2S squared. And so what we'd find is that our Ksp is actually equal to 4S cubed. And when you solve for S, it would come out to about 0.0412 molar. Okay, so now what I'm going to do is I'm going to write a Ksp equation for my other compound, Ly. So Ly solid is going to split up into L plus and Y minus ions. Now the charge on L could be +1, +2, +3, we're not really sure, right? But the charge on L that's positive is going to be equal to the charge on Y. Okay, so there's always still going to be just a 1-to-1 ratio. But again, could it be +2 and -2? Yes, but that's kind of irrelevant to the problem. Okay, so again, we're going to assume we have no initial amounts of these ions. And we're going to put our change in terms of S. And so when we write our Ksp equation, it's going to be equal to the concentration of L at equilibrium times the concentration of Y at equilibrium. So S times S. So our Ksp is really equal to S squared. Now we're told the molar solubility of these two solids were similar, right? And so we're going to assume here that they're the same, okay? And so we're going to use the S that we solved for at the top from the first compound, and we're going to plug it in for S in this bottom compound. And so basically our Ksp is going to be equal to 0.0412 squared, so the Ksp is going to be 1.7 times 10 to the negative third. Okay, so question 4 is more of an activity actually, and so it's kind of investigating the common ion effect, right? The common ion effect, which we'll again talk about a little bit more later, states that basically if you have a solid and one of its ions is already present in the solution, then the solubility of that solid will decrease. Okay, so here we're investigating the solubility of lead chloride in 4 different solutions: pure water, then a potassium chloride solution, a barium chloride solution, and a sodium chloride solution. Okay, so as you can see, lead chloride has chlorine in it, And in 3 of these solutions, right, 3 of these solutions contain chlorine, right, which is the common ion. So we know that this should decrease the solubility of lead chloride. Okay, and so really, in order to rank these, what you had to do is, as the concentration of chlorine in the solution increases, the solubility of our solid will decrease. Okay, and so that's what it says at the top, right? I ranked them. So water, which is 0 molar of chlorine, should be the most soluble in, right? In that potassium chloride solution, the molarity of chlorine is 0.15 molar, so that one should be next. In the barium chloride solution, the concentration of chlorine is 0.2 molar, right? So that's higher than 0.15 molar, so that is the next more soluble one, right? And the solution that will be least soluble is the sodium chloride solution, right? Where the concentration of chlorine is 0.5 molar. Okay, but beyond kind of understanding that conceptually, right, I wanted us to prove this. Okay, and so I only did 2 calculations. So the first one I did for water, and the second one I did for the potassium chloride. But I will explain how you would do it for the other 2 solutions, because they're extremely similar to how you would solve the potassium chloride, how I did it for that. Okay, so starting with when the solvent was water, right? So we have lead chloride, solid, that's going to split into its respective ions, right? We're going to assume we have no initial amount of our ions, and we're going to put our change in terms of S. So plus S for lead, plus 2S for chlorine, again, because its coefficient is 2. From that, we can find our equilibrium amounts of both of these ions, and we're going to set that equal to our Ksp. So our Ksp, which is 1.6 times 10 to the negative 5th for this solute, for this solid, it'll be equal to our concentration of lead times our concentration of chlorine squared. So our concentration of lead here is equal to S. Our concentration of chlorine is equal to 2S. Okay, but remember, we have to square that whole part. So it's 2 squared times S squared. Okay, and so when we multiply this whole side together, we find that the Ksp is equal to 4S cubed. Okay, and so when we solve for just S, which again is basically what is the solubility of our lead chloride, it comes out to 0.0159 molar. Okay, so what do we do when we're adding, when we are experiencing the common ion effect, right? When we're adding to a solution that has an ion present in our solid. Okay, so I'm going to start out by, again, just writing my same chemical equation, lead chloride going to its respective ions. Okay, and the difference for a common ion effect problem, right, is you're just going to have an initial amount of that common ion, right? So the initial amount of chlorine will be equal to the concentration of chlorine from potassium chloride, right? So we're told that it's a 0.15 molar potassium chloride solution, meaning that the solution is 0.15 molar in terms of just chlorine, and so that's the value we're going to use for our initial amount of chlorine. Okay, from here, the rest is pretty similar, right? We're going to put our change in terms of S, so plus S for lead, plus 2S for chlorine, and then we're going to add our initial and change sections to find our equilibrium amounts of both ions. Okay, once we know our equilibrium amounts, we're going to set it equal to our Ksp. So our Ksp is still 1.6 times 10 to the negative 5th, which is still equal to the concentration of lead times the concentration of chlorine squared, right? So the actual Ksp expression is exactly the same. What's different is just the equilibrium amount of chlorine, right? So I'm going to plug in my equilibrium amounts. So my equilibrium amount of lead is S, and my equilibrium amount of chlorine is 0.15 plus 2S. And again, remember that this whole thing is squared. Now I'm going to ignore this 2S portion because, again, it probably, especially in this chapter, it very rarely ever affects the number. And later on, I checked it and it was a valid assumption. Okay, and so that simplifies this portion to just 0.15, but again, that part still needs to be squared. Okay, I say that because lots of students, sometimes they'll just leave it off. They'll just kind of forget about it. And so please don't forget about it. Okay, so it's 0.15 squared. Okay, so now I can pretty easily solve for S, and S comes out to, or the solubility comes out to 7.11 times 10 to the negative fourth. Okay, now if you wanted to do this for the barium chloride or sodium chloride solutions, right, the only difference that you would see compared to this potassium chloride, I don't know, way of solving it, how I solved it for the potassium chloride solution, is you would just have a different initial amount of chlorine. Okay, that's the only difference. So if it was the barium chloride, you'd plug in 0.2 for your initial amount of chlorine. And if it was the sodium chloride, you'd plug in 0.5. Okay, and if you go through the calculations for the other two as well, right, I kind of listed the overall solubilities for all of them. And so as you can see, right, the highest number means it's more soluble. So as we can see from here, water's the most soluble, followed by KCl, followed by BaCl2, and then NaCl last. In those these are the solutions and the solubility of the solid in the solutions. Okay, so again, this is more of a numeric kind of proof for what we know about the common ion effect. Are there any questions on the common ion effect or any of the calculations I undertook for this problem? Okay. So lastly, we're gonna, this is kind of another activity problem. We would say in SI, we said that the addition of an acid would increase the solubility of a solid, right? That's kind of the end of chapter 16. I said, prove this using nickel hydroxide, whose Ksp is 2 times 10 to the negative 15th. And we're going to show this in a pure water solution. And then we're also gonna show it in a solution that has some HCl added to it, right? So it's gonna have a certain pH, right? An acidic pH. And then this little hint was kind of for you guys, but I think it'll make more sense when I just show how I solve this problem. Okay, so this first slide just shows how I solve for my solubility in water, right? So nickel hydroxide will dissociate into nickel and 2 hydroxide molecules. We're gonna assume we have no initial amount of either ion. We're gonna put our change in terms of S. So plus S for nickel, plus 2S for hydroxide. So our equilibrium amounts are S and 2S for our ions respectively. Now that we have our equilibrium amounts, we're going to write our Ksp expression. So Ksp, which is equal to 2.0 times 10 to the negative 15th, is equal to our concentration of nickel times our concentration of hydroxide squared. Again, remember the concentration of hydroxide needs to be squared because its coefficient in the balanced equation is 2. Okay, and so from here, we're just gonna plug in our equilibrium amounts of these ions. So S for nickel and 2S for hydroxide. Okay, and so when we end up solving for S, we find that the solubility of nickel hydroxide in a pure water solution is 7.94 times 10 to the negative 6th molar. Okay, and so on the next slide, when we solve it in terms of it in an acidic solution, we expect S to be a greater value. And it's actually an absolutely massive value. That's kind of what happens when I kind of throw out numbers, but that's sometimes what happens when you add an acid like this. And you'll see Dr. P did an example as well where his solubility came out to about 40 molar in an acidic solution. So as you can see, the molarity goes up tremendously. Okay, but let's see why it goes up so much. Okay, and so our first equation is just going to be our normal Ksp equation that we had on the last slide, right? Nickel hydroxide will split into its ions, and the Ksp of that is equal to 2.0 times 10 to the negative 15th. okay? But now that we have acid in this equation, right, it's an acidic solution, well, the H plus from our acid is going to react with the hydroxide that we produce from the dissociation of our solid to form water. And this is an extremely favorable reaction, right? Remember that water splitting into its ions, right, has an equilibrium constant that we call Kw, and that's equal to 1 times 10 to the negative 14th. Okay, but realize that this equation, where our ions are going to water, is the reverse reaction of that. Okay, so the equilibrium constant of H plus OH minus going to water is actually equal to 1 divided by our Kw, which is that 1 times 10 to the negative 14th value. And so our equilibrium constant for this equation is actually 1 times 10 to the 14th power. Okay, now eventually we're going to want to add these equations together. But when we add them together, we're going to want the hydroxides to cancel out, right? Because it's a reactant in one equation and a product in the other. And so in order for them to cancel out, right, we need to multiply this second equation, this H plus hydroxide goes to water. We want to multiply it by 2. Okay, and so 2H plus 2 hydroxides go to 2 waters, right? But remember that when we multiply an equation by a coefficient, we have to adjust our equilibrium constant. Okay, and what we do is we take our old equilibrium constant and we raise it to the exponent of whatever the coefficient we multiplied it by was. Okay, so here we multiplied our equation by 2. So our new equilibrium constant is going to be equal to our old one, 1 times 10 to the 14th, and we're going to square it, again, because we multiplied this equation by 2. This tells us that our actual equilibrium constant for this equation, 2H plus 2 hydroxides go to 2 waters, is actually 1 times 10 to the 28th, right? So an extremely high number, meaning almost all of our reactant is going to become product. Okay, now that we have this form of the equation, right, we're going to add it to our normal Ksp equation at the top. Okay, and when we add them together and cross out the hydroxides, our net equation is that nickel hydroxide solid plus 2 H plus, so 2 protons, goes to nickel 2 plus water. Okay, or 2 waters specifically. Okay, and our solubility, again, will be plus S for nickel and minus S for our solid, but we don't really care about our solid here. Okay, but it's really kind of important to note that at equilibrium, our amount of nickel is equal to S. Okay, now we want to relate this to our overall equilibrium constant, right? So what's our equilibrium constant of this net ionic we wrote? Well, whenever we add equations together, right, the new equilibrium constant is equal to the product of the equilibrium constants of the 2 separate equations. Okay, so the equilibrium constant of this overall equation is equal to the equilibrium constant from our Ksp, right? So this Ksp value, 2 times 10 to the negative 15th, multiplied by the equilibrium constant of this, this water equation, right? Our ions, H plus and hydroxide going to water. Okay, so for this overall equation, our equilibrium constant is equal to 2 times 10 to the negative 15th times 1 times 10 to the 28th power. And so our overall equilibrium constant is 2 times 10 to the 13th. Okay. And so now that we have the equilibrium constant for the overall equation, right, we are going to do products divided by reactants, okay? Remember that we don't include any liquids or solids, right? So nickel hydroxide nor water will show up. But do note that we will have to account for H plus, right? It's a reactant, so it's going to be in the denominator, and it has a coefficient of 2. So we have to square it. Okay, but our K, our equilibrium constant that we just solved for, 2 times 10 to the 13th, has to be equal to our product nickel 2 plus, divided by our reactant, hydrogen ions, and again, squared because of its coefficient. And so what we do here, right, we're going to plug in S for our nickel concentration, and for our hydrogen concentration, which comes from hydrochloric acid, right, it was 0.4 millimolar, which is equal to 4 times 10 to the negative 4th molar. Okay, so I plug in that value, I square it, and again, we solve for S, which comes to an absolutely insanely high number, 3.2 times 10 to the 6th molar. Are there any questions on this? I would be familiar. This is definitely a type of question that they could ask on the long answer. I really think that it'll kind of come down to this topic or selective precipitation. However, so I've now given a couple of examples of these problems. There's another one, part of the challenge problems, but definitely I think Dr. P did a really good job in the lecture of kind of separating the videos by topic and giving a really good example for each topic. Okay, so he goes over something like a problem like this in the last 2 lecture videos. So video 7 and video 8. So I would definitely recommend rewatching those videos before the exam. Okay, are there any questions at all before we go into our content review? Okay, and if there aren't, if people don't mind just signing in to kind of indicate that to me. Okay. And again, as always, I will try my best to check the chat throughout. However, sometimes it's hard for me to think and read and try to explain what's on this slide. So sometimes if you type a question into the chat, I'll get to it at the end of the current slide I'm on. However, if you feel comfortable with it, feel free to unmute your microphone, and I'm happy to go back and forth. It's just a little bit harder for me to explain while trying to read. Okay, so I think pretty much everyone has signed in, or almost everyone, so I don't think any questions are coming as of yet. Okay, and so we'll jump into chapter 15, which really only has 2 topics, titrations and buffers. Okay, and on your exam on Friday, I would expect you to have 1 question of each, a single titration question and a single buffer question. Okay, could they do some other layout? Potentially. I'd expect your exam to be 3 to 4 questions. I really would anticipate 1 question being titration, 1 buffer. Okay, and then the other 1 or 2 questions, chapter 16. Okay, now I've kind of taken some of the fluff out of titration, so if you want a little bit more background, definitely go back to when we originally covered this, but I'm really trying to talk about titrations in reference to how you'll see them on a long answer exam. Okay, and so we really only see 2 types of titration questions. We see strong titrations, and we see weak, strong titrations. Okay, now remember in titrations, we have 2 chemical species, right? 1 will be an acid and 1 will be a base, right? You'll never have a strong base and a strong base. That's just won't happen in a titration, right? They always need to be opposites. So you might have a strong acid and a strong base titration. You could have a weak acid and a strong base titration. You could also have a weak base and a strong acid titration, right? But those are really what you can see. Okay, just some like miscellaneous notes for you. Remember the term equivalence point, right? And the equivalence point is when our moles of H+, right, moles of our acidic species equals moles of hydroxide, which is our basic species. Okay, that's really a key concept. Okay, another really key point is what we see during titrations, and this is really important, is that really the whole concept of it is our acid and base portions will neutralize each other. right? If you have a weak acid that's being titrated by a strong base, right, you're going to add hydroxide to the solution, and the equilibrium from your weak acid is going to shift in order to produce hydronium that will neutralize the hydroxide you added. Okay? And then a big reminder that whenever you do a titration question, always start with moles. Okay? Depending on the scenario you're in, you might need to later convert to concentration. Okay? But always start off with moles in titration questions. Okay? Do not plug molarity straight in. Okay? Because typically your acid and base portions have different volumes. And because they have different volumes, you can't just compare concentrations. You know, you have to convert to moles and compare moles. Okay, so I'm just going to kind of briefly talk about strong titrations, and I think, and then weak strong titrations. I definitely recommend later on, maybe write this down or take a picture of it, but definitely later on, look at an example with my notes next to it. I think it helps clarify a lot more, especially the notes I'm going to give you on weak strong titrations. Okay, now strong titrations, I would definitely recommend to be familiar with them. However, if I were a betting man, I would put my money on the fact that on the exam you will have a weak strong titration. Right, they're harder to do, weak strong titrations, and year after year, that's what they give students on the long answer exam. It does not mean they couldn't give you a strong titration. However, it is much less likely. Okay, so whenever you have a strong titration, you really only have two scenarios, right? And remember, strong acids and strong bases completely dissociate, right? So really, you're just going to have H+ or OH-. Okay, so your first scenario is you will have more moles of H+ or OH-, right? It could be either. It just depends on, you know, which portion you have more moles of. Okay, but one situation is you're going to have more moles of H+ or more moles of hydroxide. And so what your first step is going to be to solve for excess moles of H+ or OH-. Okay, so let's say that we have 1 mole of H+ and 0.5 moles of hydroxide, right? In order to solve for excess moles of H+, because there's more H+, we would take the 1 mole of H+ and subtract from it 0.5 moles, because that's how much hydroxide there is. That would leave us with an excess of 0.5 moles H+. Once you have moles of excess H+ or OH-, you're going to divide that number of moles by your total volume, okay? And this is to convert it from moles to molarity, okay? It is important that you convert to molarity here. Now, one thing I really emphasize total volume. One thing to be very careful of is, right, there's going to be a volume associated with our acidic species, right? So if we add a strong, you know, we might have 100 milliliters of a strong acid and 200 milliliters of a strong base. Okay, so it's really important that when you convert to molarity that you use your total volume, which in the little example I gave is 100 milliliters of acid plus 200 milliliters of base for a total volume of 300 milliliters or 0.3 liters. Okay, again, that's something that kind of in the stress of an exam, you kind of might forget about, but be very conscientious of that. Okay, so at this point, after this bullet point, you will have molarity of H+ or molarity of excess hydroxide. Okay, if you have the molarity of excess H+, right, you can take the negative log of that value to immediately find your pH. Okay, and they'll be asking for your pH, so that would be your answer. If you have excess hydroxide, right, you would have solved for the molarity of hydroxide. And so you can take the negative log of your concentration of hydroxide to find your POH And once you have that pOH value, you can pretty quickly find your pH, right? Remember that these two, pOH and pH, always add up to 14. Okay, and so that's the first scenario for a strong titration, right? You would have more moles of H plus or OH minus. The only other circumstance or scenario you can run into is if you have equal moles of H plus and OH minus. Okay, and by definition, if you have equal moles of H plus and OH minus, you are at the equivalence point. And if you ever saw this on an exam, you might want to have a quick second to celebrate because you actually have to do zero work. Okay, if you have, and it has to be for a strong titration, right? It does not work for weak strong titration. But if you have a strong titration and you have equal moles of H plus and OH minus, your pH is 7. No work required. Just show that they're equal moles and just write pH 7, circle it, and move on. Okay. Are there any questions on strong titrations before we move into weak strong titrations? Okay, and again, I would recommend going back to when I've covered or a professor's covered strong titrations and kind of look at these steps in reference to an actual problem. I just don't think we have enough time to do that tonight, which is why I didn't bring my own for it. But I think it would be very beneficial. Okay, now let's look at weak strong titrations. Now I would very much expect this to appear on your exam as a 3 or 4 part question, okay? And so whenever we have a weak strong titration, oh, I think there might be a question. Ooh. I have no idea when I went over them. I commented under many of my videos. It probably would have been the first time I covered chapter 15, but off the top of my head, I definitely cannot remember. So weak strong titrations, again, I would very much expect this to be the problem on the exam. You have 3 general situations, okay? And here I'm going to provide, again, kind of a stepwise mechanism to solve these problems. Now, it's really important to note that these steps only apply to their specified scenario, okay? And so I actually think that during titration problems, the most important step is to identify which scenario you are in. And again, I recommend after this session to look at a weak strong titration and compare the problem to these steps. I think it will really cement, especially if you're not feeling that comfortable with solving these yet, I think it will really cement the process needed to solve for the pH. Okay, so our first scenario is before the equivalence point. And you are before the equivalence point anytime you have more moles of your weak acid or base, right? It doesn't, you know, it just depends on the situation. They could give you either. If you have more moles of that weak species, then you have moles of the strong species, okay? So if you have more moles of weak than strong, it's automatically before equivalence point, and these steps can help you get the answer every time. Okay, it's really just kind of understanding what I'm trying to say through these steps. Okay, and so what you're going to do is you're going to start out by writing your ice table, right? And you know, you'll write ice down the side, and you're going to have an initial amount of that weak acid or base, right? For this current example that I'm talking about, let's pretend that we have a weak acid and we're titrating with strong base. Okay. Now, the moles of strong species added, which if we have a weak acid, the mole of strong species will be titrating it with a strong base. So the moles of hydroxide that we add will represent the change in our ice table, right? So we'll have, so if we add 0.1 moles of hydroxide, right, we would add 0.1 moles to our product side in our ice table, and we'd subtract 0.1 moles from our reactant side. Okay, now that we've input the change into our ice table, right, we can solve for the equilibrium amounts of both our weak compounds. So in my example, the equilibrium amount of our weak acid and our conjugate base, right? You'll have an equilibrium amount of both your weak acid and your conjugate. Again, this is assuming you start with a weak acid. Okay, now that you have equilibrium amounts of those, you can actually use your Henderson-Hasselbalch equation to solve for your pH, right? So you're going to need to find your pKa based on your Ka, but you can basically just plug in those equilibrium amounts of acid and conjugate base, and that will directly get you the pH. Okay, and again, you can use these steps anytime you are before the equivalence point. Okay, but that's why it's so important to identify which scenario you're in, because you do not want to use the wrong set of steps, or a set of steps for the wrong situation. You will not get the right answer. It was asked, if you have ice table with H3O plus as a product, could you take the negative log of that concentration to find pH? I would guess no. I would guess no off the top of my head. I would definitely check, is it possible? Maybe, but I would definitely recommend using the Henderson-Hasselbalch equation. Because when you add to, again, if you start with a weak acid and hydronium, H3O plus, is a product, right? Your change for hydronium is the value equal to the amount of hydroxide you added. So really, you're creating hydronium to immediately react with hydroxide to form water. So in essence, at equilibrium, you actually have 0 hydronium. Again, because it's all being used to react with the hydroxide to neutralize it. So I really recommend always using the Henderson-Hasselbalch equation. Okay, did that explanation make sense to people? Yeah, personally, I'm not saying I've never really tested that, to be completely honest, but I don't think it would work. Okay, so again, I really recommend the Henderson-Hasselbalch equation. It's kind of the best equation in this course. It helps you a lot. Okay, so now let's look at our second circumstance, right? So our second circumstance is when we're at the equivalence point. How do we know if we're at the equivalence point? Well, we know we're at the equivalence point if the moles of our weak acid are equal to the moles of our strong base, right? So equal number of moles of each. Okay, so once we identify that we're at our equivalence point, we're gonna write our balanced equation in our ice table. And again, we're gonna input our initial amount of our weak acid. Again, when I'm assuming we're doing a weak acid strong base titration. Okay, now the moles of our strong species, in this case, hydroxide, the amount of moles of hydroxide added will represent the change in our ice table. Okay, and whenever you're at the equivalence point, right, you'll notice that all of your weak species, so in this case, all of our weak acid, will be converted into conjugate base in this case, right? So at equilibrium, the amount of weak acid that you would have would be 0. Okay, it would have all been converted into product. Okay, because you have 0 of your starting weak species, in this case weak acid, and you do have some of your conjugate base, whenever you're at the equivalence point, you're actually going to have a reverse ice table. Okay, and so what you're going to do is you're going to take that conjugate from your first ice table, so that conjugate base, and in this new ice table, you're going to write it as a reactant. Okay, and you're going to react it with water to create your conjugate acid and hydroxide. Okay. So again, your conjugate, you're going to react with water in your reverse ice table. Your conjugate is now going to be a reactant. Okay. And so your conjugate, right, which is now on the reactant side, will have some initial amount. right? And so you'll write your ice table and you'll write your change in terms of X. So plus X for products, minus X for reactant, and you'll write your equilibrium amount in terms of X. Okay? Now this next step is super important, and I think people forget about it a lot. When you have your equilibrium amounts of X, realize that in titration questions up to this point, we use moles. Okay? But to go further and eventually solve for X, we need to convert our equilibrium amount of moles to molarity. Okay, and so let's say at equilibrium, your amount of conjugate base is 0.1 moles minus X. Well, you have to take that 0.1 moles and divide it by the total volume, right, in order to convert it to the molarity. Okay, and so if the, let's say the total volume is 0.1 liters, right? 0.1 moles divided by 0.1 liters would tell you that it is 1 molar minus X, right? The minus X part stays, but you have to convert from moles to molarity. Now that our equilibrium amounts are in terms of molarity, right, we can use the Ka or Kb in order to solve for X, right? And X will represent a concentration of hydroxide or a concentration of, concentration of H plus or a concentration of hydroxide, right? Again, which one you get is dependent on if you start with a weak acid or a weak base. Okay, now you might ask yourself, how do I know when I should use my Ka and when I should use my Kb? Okay, and to know which one you should use for that, you have to look at your reverse ice table. Okay, whatever is on the reactant side in your reverse ice table, right, whether it's an acid or a base, that's which one you should use, Ka or Kb, right? So in the instance where we have a weak acid being titrated by a strong base, right, our conjugate will be a conjugate base in our reverse ice table. And so if our conjugate base is on the reactant side, right, a base is on the reactant side, we have to relate it to Kb, okay? If in our reverse ice table, it's a weak acid on the reactant side, then we'd use Ka, okay? And so from here, you just normally solve for X, which again will be our concentration of H plus or our concentration of hydroxide. And then depending on which one of those you have, you can solve directly for pH, or if you have hydroxide, you can solve for POH, and then from there, convert to pH. Are there any questions on at the equivalence point? Okay, so we're gonna go to the last circumstance, which is past the equivalence point. So in this circumstance, our moles of our weak acid or base is going to be less than the moles of our strong acid or base added. So again, we're gonna write our normal equation in our ice table. Okay, and our change, right, in this case, we're adding more strong species than we have of weak species. And so we're actually gonna convert all of our reactant into product here, right? And again, the goal of that is to neutralize as much of the strong species or strong hydroxide that we've added, okay? But you'll notice that you still have more of that strong species, right? So again, if we added hydroxide, you'll notice there's still more hydroxide than hydronium that we were able to produce. And we produce that hydronium by converting all of our reactant into product. Okay, and so what we do here is we solve for our excess moles of H plus or OH minus, right? So if we add 2 moles of hydroxide and we convert all of our reactant into product, right, in our equilibrium for a weak base, and we can only produce 1.5 moles of hydronium, right? 2 moles of H plus minus 1.5 moles of 2 moles of OH minus 1.5 moles of H plus would give us 0.5 5 moles of excess hydroxide, right? You're just solving for how much excess there is. Once we have excess moles, we're going to divide it by the total volume to convert it into molarity. And then lastly, based on our molarity of H plus or OH minus, we can solve for pH directly, or if we have hydroxide, we can solve for pH indirectly by first finding our pOH. Again, I highly, highly, highly recommend going through these steps again while looking through a problem, whether it's a problem I've given. I'm going to give one tonight during the challenge problems that I think would be great to look through with these steps. It could be one your professors have given. Hopefully this is just gives you a little bit more confidence in how to solve these problems. Okay, but again, the key is correctly identifying which of the 3 scenarios you're in, right? Anytime you're past the equivalence point, you can use these steps. Okay, any questions before we move on to buffers? Okay. Now I don't have too many notes on buffers and definitely nothing new, right? So just remember what buffers are for. So buffers can resist not only the addition of acid, but also the addition of base. Okay, so it actually resists both. And the reason why it can resist both is because all buffers contain 2 chemical species, right? They're gonna contain a weak acid, and they also need to contain the conjugate base. Okay, so they're gonna start out with both. Okay, now there's 2 ways that we typically see these buffers come to fruition. The first is you add a weak acid to a beaker, and you also add the conjugate base in terms of a salt. Okay, so maybe I'll add into a beaker hydrofluoric acid, and then I'll add potassium fluoride. Okay, now it's really important that when you see something like potassium fluoride, you can recognize that that's the salt of your conjugate base, which is F minus, and you kind of recognize that the potassium, that K, is irrelevant, right? You have HF and F minus, right? The acid and the conjugate. That's really important. Okay, so that's one way you can create it. You can also create a buffer solution by partially neutralizing a weak acid-base with a strong base or acid. Okay, so basically what this second point is talking about is you can create a buffer. It's basically a titration question where your circumstance corresponds to, or your scenario corresponds to before the equivalence point, right? Look at any titration where you are still before the equivalence point. You will have at equilibrium some concentration of weak acid and some concentration of conjugate base, right? Both are present, and so that solution that you've created will be a buffer. Okay, again, key points, your equilibrium will shift in order to neutralize, right? So if you add H plus, your equation is going to shift to create hydroxide to neutralize the H plus. If you add strong base, so you're adding hydroxide, your equilibrium is going to shift so that you create more H plus, and again, that H plus will neutralize the hydroxide. That's really the big key concept behind buffers. Say some other notes about buffers. I would always recommend for pretty much every buffer problem to use the Henderson-Hasselbalch equation. I'll talk about it more on the next slide. But something to point out is that the acid and our conjugate base are in the same solution. Okay, so when you're using the Henderson-Hasselbalch equation, you can plug in either moles or concentration, right? It's because the volumes are the same. You can plug in either to the Henderson-Hasselbalch equation, okay? You just have to remain consistent, right? You can't plug in moles for your acid and concentration for your conjugate base, right? You have to plug in moles of both or concentration of both. But either way, you'll get the same answer. Okay, so again, listed here, and I'm sure by now you're very familiar with it, is the Henderson-Hasselbalch equation. it is truly your best friend for chapter 15. It makes your life so much easier. Okay, and so it's your pH is equal to your pKa, which is the negative log of that Ka value, plus the log of your concentration or number of moles of conjugate base divided by moles or molarity of our acid, our weak acid. Effectiveness of a buffer, for the most part, I think a lot of these points are kind of more multiple choice key points, what makes it more effective. So having larger concentrations of your conjugate base and acid makes it a better buffer. It is more effective if it's buffering at a pH close to its pKa. That's another point. But I'd say the big point to keep in mind, not that these things aren't important, but remember buffering capacity, right? So each buffer it's only really good at doing its job, right? It's good at resisting pH changes within a very narrow range. And we say that that range is equal to the pKa plus or minus 1. Okay, and so if your pKa is 6, right? Some acids pKa is 6, it would be good at buffering between a pH of 7 and 5. Okay, but outside that range, it wouldn't be good at buffering, right? If you added acid or base, it would rapidly change the pH. While within that range, it would change the pH very slowly. Okay, any remaining questions before jumping into chapter 16? Okay, so all of this is pretty recent. We've gone over it pretty recently, so I'm not going to talk too extensively about these topics unless there are questions. I definitely recommend or am happy to answer any questions on any of these topics. But we learned in chapter 16 about Kf, which we call a formation constant. Okay, and so basically we're going to use Kf whenever on our reactant side we have some ions or some simple compounds. And on our product side, we'll either have a solid or we can have a complex ion, right? And how do you know if you have a complex ion? Complex ions typically have a metal, then some other group that might be in parentheses. It could be something like ammonia, could be something like cyanide, that's also common to see. And complex ions also typically have a charge and are in the aqueous state. Okay, so Kf, just like, pretty much like any other equilibrium constant, is products divided by reactants. Okay, so in the case where you are forming a complex ion in the aqueous state, do remember to include that in your equilibrium calculation. Okay, so again, products divided by reactants. And again, remember to raise the concentrations to the coefficients, right? So the concentration of ammonia here would have to be raised to the 4th in our Kf equations. Okay, and we often form these complex ions during a Lewis acid-base reaction. That's definitely a very small little note just to kind of keep in mind. With the metal being Lewis acid, so in this case copper, and the covalent compound, in this case ammonia, being the Lewis base. And remember that Lewis bases by definition need to have a lone pair, right? Which makes sense, ammonia has a lone pair. Now, I'm sure you're much more familiar with this. We use it in so many calculations, our solubility product constant, or you'll just hear Ksp. And this is for the dissociation of a solid into its ions, right? We learned in this chapter that pretty much every solid dissolves at least partially in water. And so that's what this is calculating. And yeah, and really just for when you're looking at problems, just note that for our ice tables, instead of using X, we kind of use S for solubility in this chapter, but really they're interchangeable. It's just in case you're wondering why we use S often. So common ion effect, this is something that we actually proved in one of our challenge problems, number 4, earlier in this session. But basically, the common ion effect occurs any time we add, where any time a specific ion comes from multiple chemical species. Okay, and so in this chapter, right, we'll see the common ion effect when we add a solid, right, so the solid that will have a Ksp, one of the ions in that solid will already be present in the solution, right? So in example number 4, from our challenge problem review, we added lead, I believe it was lead chloride. That was a solid, and we were looking at its solubility in different solutions that had different concentrations of chlorine. Okay, so the chlorine was added to the solution as a salt, which dissociates completely, and we saw that it impacted the solubility of a solid. Okay, and so what the common ion effect actually says is that if there is a common ion, it will decrease the solubility of the solid, right? So we proved that again in number 4, that lead chloride had lower solubilities when the solution it was added to had higher concentrations of chlorine, which was the common ion, right? And another example, barium fluoride, for example, would be more soluble in pure water than 0.1 molar of a sodium fluoride solution, right? Because sodium fluoride has that fluorine common ion. Just to talk about precipitation, right? So if we don't know if we're at equilibrium, we're technically going to plug in values for Q, right? We're going to talk about this more on the next slide with selective precipitation. Okay, but when Q is less than our K, right, or our Ksp in this chapter, that means the forward reaction is favored, right? So looking at a normal Ksp equation, if our forward reaction is favored, we will continue to dissolve our solid into its respective ions. Okay, if our Q is equal to our Ksp, that means we're at equilibrium, we're at saturation, and we've really dissolved, or the solution holds as much ions as it possibly can. If our Q is ever greater than our Ksp, our reverse reaction will be favored, meaning our ions will combine to form precipitate, right? That's what we will see in the selective precipitation problems, right? Which we'll cover one tonight as part of the challenge problems, right? But basically, in our selective precipitation, we add a certain amount of one ion through a salt, a certain amount of another ion through a salt, and basically, if you multiply them and the Q is greater than the Ksp, then precipitate will form, right? So in the selective precipitation problems, we're basically solving for the concentration of an ion needed to be at Ksp, okay? And the reason why we do that calculation is because as soon as the concentration goes above the Ksp, then that precipitate will start forming. Okay, and just some general terminology. Unsaturated means that more solid can be dissolved. Saturated means that as much solid is dissolved as it possibly can. And supersaturated means that basically too much solid is added. As much that can split into ions that will, but there's just too much solid. So some excess will accumulate on the bottom. Okay, and then dissolution equals dissolve. Okay, I think there's just about 2 slides left. Sorry, I know I'm going a bit over. So selective precipitation. So basically in this circumstance, right, there will be several different cations, or it could be anions as well, but typically it's cations. So ions with a positive charge, right? And they can form solids with the same anion, right? So think back to question number 2 that we went over, I think it was. 1 and 2, where it was copper iodide, right? That had a Ksp, and lead iodide, right? So both copper and lead, two different cation, could form a solid with the same anion, which was iodine or iodide. Okay, and so in the typical problem, they'll ask you which solid precipitates first. Okay, and then you'll typically be asked what percentage of the ion that participate first has precipitated or is in the form of a solid when the other ion starts to precipitate. Okay, if that's confusing, challenge problem 3 from tonight directly hits on this point. I definitely recommend you all trying it. Okay, because in my personal opinion, if I were to write the exam, again, I would make 3 or 4 questions. I'd make 1 titration question, 1 buffer question, and then I would have 1 or 2 chapter 16 questions. Okay, I think selective precipitation has a massive chance of showing up on Friday. Okay, the other topic that I think could definitely show up, and maybe both of them will show up, but the other topic that I definitely think could show up is increasing solubility, right? So this was like the last challenge problem we went over tonight. And again, this corresponds to the last 2 lecture videos gone over on this chapter. Okay, and basically we learned that you can increase the solubility of a solid through 2 mechanisms. The first is you could add a strong acid, okay, or you can, create an acid. Okay, and basically what happens is the addition of the acid will react with the anion portion from your solid, right? So your solid turns into some of its ions to some extent, and the portion, the ion with the negative charge, will react with H+, and their reaction causes more of the solid to dissolve into its ions. Okay, and we often see this with solids that contain hydroxide, carbonate, sulfide, or phosphate. The other way you could see this, and this was covered, this other point is covered in the last video, that video 8 from this chapter, is when you form a complex, right? So instead of adding an acid and having your second equation being kind of an acid-base equation, your second equation would be like a formation equation. Okay, so maybe ammonia will react with the metal cation, which comes from the dissociation of your solid, and the combination of these together forms a complex ion, right? And so the desire to form this complex ion kind of, again, pulls your reaction forward and causes the solubility to increase of your solid. Okay, and again, it really utilizes Le Chatelier's principle. Okay, and so my last slide is just kind of a picture showing this, right? So this is an example of adding an acid, right? So if we have calcium hydroxide, it'll split into calcium and 2 hydroxide molecules. Well, if we add acid to this scenario, right, the H+ from the acid will react with the hydroxide in our first equilibrium, and these will preferentially form water. Okay, and so because H+ is reacting with OH- to produce water, really the concentration of hydroxide on the product side in this equilibrium is getting driven downward. Okay, and based on Le Chatelier's principle, if the amount of the amount of product we have is decreasing, we will counteract that change in equilibrium by shifting to the product side. Therefore, more solid will dissociate into ions. Okay, the last point I want to make about this is that when you write your overall equation, so when you combine these 2 equations, remember that each of these equations have their own equilibrium constant. Okay, and so when you write your overall equation, you have to find for this overall equation its equilibrium constant, which you do by multiplying the equilibrium constants of the 2 above reactions. Okay, so if this is K1 and K2, the equilibrium constant from this, for this overall equation, would be K1 times K2. Okay, so I'm just going to show these questions. Again, there are 4 long answer questions. They are extremely intensive. Okay, they're a lot of work. I kind of wanted to just ask 4 questions instead of way more. But because of that, I really wanted to hit as many potential things as they could ask you. Okay, so for a titration question, I would not expect them to give you 5 points to solve the pH for. I would expect 3 or 4. Okay, I can say that back on my exam, I had 4. Okay, so if you think 4 is too much, they have given that definitely in the past. But I would expect a titration question where it's a weak acid or base with a strong base or acid, and I would expect at least 3 different points, if not 4. 5 is probably a bit much. Okay, so here's the first example. The second question is a buffer question. And so again, this is a very intensive, long buffer question. I would not expect them to give you all 3 parts like this. They could give you maybe 2 of these parts, right? So part A is your very classic kind of question. And then part C, so B and C are kind of testing your knowledge of adding acid or base, how that shifts your equilibrium, and also test your knowledge of buffering capacity. Okay, one part that I want to emphasize is for parts B and C, do them separately, right? So for part C, so you're going to do part B and then you're going to try part C. When you do part C, pretend part B never existed, right? Disregard part B. I want you to use the initial amounts from the beginning when doing part C. Okay, but again, a very, very intense buffer question. 3, this is a selective precipitation question. So again, I think this is extremely likely to show up on the exam. Very, very likely. I would say that this is harder, or I believe harder than you'd see on the exam. However, the questions I ask are probably the same that they would ask on the exam, right? They basically ask what order do our solids appear in, right? So precipitates, what order? And then when the final one precipitates, what percentage of each cation is present in the solid, in its respective precipitate? Those are the questions I would expect you to get. However, the reason why I think this one's slightly harder are there are 4 different solids that you can form. And really, I guess it's harder is a bit misleading. This is just a lot more work than they would have you do. And the reason why I made it this way is it's just very, it's a lot of repetition, which I think when trying to, gain more confidence and skill in these calculations, that can just be beneficial doing it a couple more times. Okay, but the actual difficulty of the calculations would be the same as the exam, I believe. Okay, and then a student on Monday asked me if they could ask you basically for a pH or how much H plus to add in relation to an increasing solubility problem. And so I'm basically taking the problem that we did or went over at the very beginning, challenge problem 5, and I just changed it slightly, right? We're still looking at the same question, but here I'm asking what pH would be required if we want the solubility of nickel hydroxide to be 1 molar. Okay, now when the student asked me about this type of problem on Monday, I had said that honestly, I'm unsure if I've ever seen a problem like this. And I stand by that. I don't really know if I've ever seen a problem like this given in this class. However, after kind of investigating the problem a bit, it is possible. Okay, so I kind of wanted to give it to you as just something a little bit new and different. Okay, but those are the 4 challenge problems. It's actually my mom's birthday and I need to call her. So I am unsure when I'm going to record this. Sorry, I see your question, Victoria. I'll get to it in 1 second. I'm unsure when I'm going to record this. I might be able to record it tonight. If not, I think I will be able to record it tomorrow morning. However, either way, it should be up by noon tomorrow, okay? I'm not going to completely promise that I'm going to be able to get it up tonight. I still have a bunch of other things that I need to do, but I do promise that it'll be up by noon tomorrow. Okay, this video of me going over the content will be uploaded tonight. However, again, recording all of this for these 4 problems, I have so many pages of work for it. That might not happen until tomorrow. Okay. And so are there any questions besides Victoria's? I do see yours, Victoria. I'm probably just going to end the recording, but then I will come back in. Actually, I can end the recording here. So I'm going to end the recording, but any questions, I'm happy to answer.